Hello there guys, this is Vignan. Welcome back to another video on Introduction to Memoization in Dynamic Programming. So here I've taken a small example called Fibonacci sequence. This function, it returns Fibonacci sequence. For example, if you give 5, it'll return the fifth sequence of Fibonacci numbers. And I'll explain you why I've taken this example. But first, let's see what Fibonacci numbers are, okay? Let's take two basic numbers like 0 and 1. Let's try to add these two. If I add 0 plus 1, it's going to be 1. And if I add 1 plus 1, it's going to be 2. And if I add 1 plus 2, it's 3. And if I add 2 plus 3, it's 5. And if I add 3 plus 5, it's 8. If I give indexing, this is going to be 0 number, this is going to be first number, this is second number, this is third number, this is fourth number, this is fifth number, this is sixth number. So if I try to run this program, and if I give the input as like 6, let's see what it returns, okay? It's building, just give me a second. So if I give 6 over here, it has returned 8 as the output. Why is that? It's because the sixth sequence is 8. And if I give 4, it should return 3. Let's run this. If I give 4, it should return 3. And let's give 4, it did return 3. Okay? So I hope you understood what Fibonacci sequence is, right? And what does function do. Now let's try to break this down, okay? So why did I take this as an example? But let's try to see what it's doing if I pass 3 into this number, okay? If I pass 3, let's if I pass 3, what's going to be output? The output is 2. And why is that? Let's see. Um, if I pass 3, it's going to return f of 2, because it's going to be 3 minus 1 plus f of 1. Why is that? It's because this line is going to get executed, okay? And f of 2 is going to be, again, f of 1 plus f of 0. And we have reached our base condition. And if you check over here, if it's less or equal to 1, it's going to return either 1 or 0. So this is going to return 1 plus, and this is going to return 0, which is going to be 1. And f of 1, as we know, it's going to return 1 again. So this is going to be 1 plus 1, which is like 2. And that is why this, when the input is like 3, the Fibonacci is like 2. The Fibonacci output is like 2. Uh, okay, it's working fine. But let's try to give a big number, okay? Uh, let's try to give a big number. I'm gonna give like 10. Oh, it's 55. Okay, let's try to give even more bigger number. Like 30. It's like 83240. What if I give 40? Actually, let's check with 40. Oh, there. If you see there's a bit of delay. If you see there's a bit of delay, why? If you see there's a bit of delay. If I say 30, there's a bit of delay, and if I give, oh, where's what happened? It's not running. Let's try to rerun this. Oh, I don't see the console. Oh, there's the console. If I give 30, there's a bit of delay, and if I give 40, there is a bit of delay if you see. It's taking some time and it did return the output. Why? If you can observe, this is forming as a tree. This is forming as a small tree. So if you guys have studied a bit of time complexity or data structures or algorithms, you can clearly say that it is taking 2 to the power n times to calculate this. And as you know, uh, oh, I'm sorry, I'm gonna still keep the tree. As you know, 2 to the power n is a big and not is what we want. It's a big number. We need something like n or log n to compute it a bit fast. So what can we do actually if we clearly observe this tree? I would say if you see there is one over here and there is one over here, right? I mean it has been seen 2 times. I'll take one more example. For an example, if I take Fibonacci of 4 for the same thing, it's gonna repeat like f of 3 plus f of 2, and it's gonna return f of 3 is like f of 2 plus f of 1, and f of 1 is gonna return, I mean f of 2 is gonna return again f of 1 plus f of 0. Okay, f of 1, this gonna return 1 because we have the base condition. This gonna return 1. And if you see, this 2 is also coming over here. If you clearly observe, this 2, this 2 is going to return the same value, right? So why am I computing 2 times? Why? I've seen the same tree over here, and this tree is going to be also be the same thing. So what can I do? There's a famous quote, right? History repeat itself. So memoization is used when you see the same problem coming again and again and again. And what if I feed this value somewhere and I try to reuse this? Let's say I store this value after computing once and I reuse the same value over here rather than recomputing. So that's going to decrease some time complexity. That's going to decrease the calculations. For that, what I can do is uh, I can I can take an array actually. You know, I can take a small array over here. I mean, let's say I would say I would take a small array, int array. I'll say it as memo. Okay, I'm gonna say new n plus one. So I'm gonna take until the n's plus one input. Okay, and then I'm gonna say dot fill. I'm gonna fill everything with minus one. Okay, by default. Okay, and I'm going to modify this function. I'm going to pass this memo and memo over here. Okay, and let's pass the same memo over here 2 times. Um, okay, now what I'm gonna do is I'm gonna check if it's already been recomputed. I'm going to check if f2 is already solved. It's already there, which is not minus 1, and it has some value. Okay? Like, I'm going to say something like, I'm going to check if memo of uh, n not equals to -1. It means that the value has already been computed. So I'm going to simply return the value. And I'm going to return the value, memo of n. Okay, now you guys get it? Which means that this tree is not being calculated twice. It has been calculated over here, and I'm using the same value to not recompute, actually. Else, what I'm going to do is, I'm going to say memo of n equals this. Let's try to run this. Oh, there are some errors. Let me check. Oh, I need to pass this error. I'm really sorry. Uh, okay. Okay, let's try to run this. I'm gonna give 40. If you see, it's really quick. If you see, it's really quick compared to this and this, right? If I give 30, it's still quick. I'll do one more thing. I'll just try to copy paste this. Okay. I'll paste another function over here, and I'm gonna say it as like memo fib. Okay. And I'm gonna remove this thing over here. This is the old function. Okay. Okay. This is the old function. Uh, I'm gonna say memo fib over here and memo fib over here, and let's try to let's try to compare the old and the new one. Okay. Uh, let's try to run both. Okay. Let's try to run both at the same time, some way or the other. Okay, this is like memo fib, and I'm gonna pass memo in this, and this one is unoptimized. Okay, this time complexity is 2 to the power n, and this time complexity over here is n. Okay, let's try to run both. Okay, let's go. I'm gonna give 40 as input. You see that? The first one is really fast. The second one has taken some delay. Why? Is because this one is recomputing the same problem, which is unoptimized, which is to the power n, which is brute force, and this one over here is optimized, and it runs really fast. If I rerun this again, and if I give 30, if you see, this came fast, this came a bit slow. If I'm giving like 35, there's not much of a delay. If I give 41, oh, this came a bit fast because it's optimized. This one is still computing, but it is returning the value. So the point of top-down method or memoization is if you see an lapping sub problem, don't try to recompute it. Try to compute it once and reuse the same value if the same problem arises again. Thank you. Guys, if you like the video, please leave a like. And I'm excited for making up more videos. Thank you.